This is a nice demonstration of Archimedes' principle. It states that the buoyant force on an object submerged in a fluid, whether that be air or in this case water, is equal to the weight of the displaced volume, okay, that comes out of the position of where this object once was. So what I have here is a 1 liter block filled with a little bit of metal so that it does sink, and I have a container above it that it's attached to that it's also 1 liter. So this is the same volume as this block. Now these are tied to each other and their total weight in newtons is about 11. So that's the total weight pushing down. There's no buoyant force or no significant buoyant force here until we go into the water. So I'm going to lower this down now, and we should see that as I drop this, that the buoyant force, okay, should take some effect and do something with our scale. In fact, the scale should be reading a much lower weight now because we now have the weight of the water that was once where this wooden cube is rushing in, pushing upward. And notice we're about 1.5 newtons here, which means that we have about 9.5 newtons of buoyant force. That buoyant force upward that's making this be less than 11 must be equal to the weight of the water that was being displaced. So what I'm going to do is add back the water to this system that's now pushing back and creating a buoyant force. So I'm going to add the weight of water to cancel out the buoyant force and show you that the original newtons that we got here should be back to 11 by adding back the weight of the water. Almost there. And now we're back to approximately 11 newtons. It's not all the way filled yet. There it is. Okay? To show you that clearly the weight of the displaced fluid is in fact that buoyant force because I added the water back. A nice way to represent Archimedes' principle.